So, this last video in this course on computational systems biology, I will basically try to recap the entire course. I will just try to list a number of concepts that we have studied all along, beginning from the fundamentals of mathematical modeling to graph theory to ODE modeling, parameter estimation, metabolic network modeling, for which we dedicated quite a big chunk of our time, flux balance analysis, perturbations and so on, and finally up till regulation of networks, Boolean network models, and some scattered advanced topics like robustness, evolvability and so on. Where did we start off? We started off with basic fundamentals of math modeling, right. So, what are the most important thing to remember here? Always remember your assumptions, and yes, and remember that all models are wrong, right. Okay. So, quote by Box, the great statistician. Right. So, we first looked at the fundamentals of mathematical modeling. We quickly looked at some representations of networks and so on, but essentially moved over to network biology. What are the important concepts in network biology? The parameters and topologies or network models, essentially Vedoshreni, Walsh-Strogatz, Barabashi-Albert, there are many more which we did not look at, right. And then one very important concept here was the centrality lethality hypothesis. And then how do you perturb and study networks, followed by network motifs. So, very important concept we learnt in network motifs was how do you build a null model, and how do you bootstrap networks, rewire networks to generate additional networks to mine for statistically significant motifs and so on, right. And then we quickly took a detour and looked at reconstruction of models. This is quite challenging, involves a lot of effort, and we looked at metabolic networks and also protein protein interaction networks, and this is where we studied about things like phylogenetic profiling, Rosetta Stone and so on, right. So, this is a very important aspect that one needs to be aware of while working with systems biology models, right. And following this we went to dynamic models. So, how do you build dynamic models? You basically start with a picture and try to catch hold of every interaction that is happening there, right, and find out what kind of kinetics. So, you need to know your basic kinetics, right, and again remember the assumptions. There are interesting concepts like identifiability that one needs to be aware of, but it is not something that we could cover in this course, but there are courses that will talk to you about linear systems, identifiability and so on. And importantly, we also looked at how do you solve ODEs, even stiff systems, and most importantly for any systems biologist, the concept of parameter estimation wherein you need to worry about multiple things, right from crafting a good objective function all the way up to finding the correct direct search algorithm, right. And we did look at simulate annealing, GAs, so on, right, and some sensitivity analysis is also necessary, right. And you can think of global and local sensitivity analysis. Following this, we went to constraint based modeling. This was obviously a constraint based approach, but the main constraint that we exploited was stoichiometry, and all through this module we looked at dx by dt equals SV equals 0, right. This was the heart of the whole thing, and we looked at LP, which was FBA, quadratic programming, which was MoMA, other techniques like FSEOF for predicting overexpression and so on. We could also use MoMA for predicting overexpression and so on. And these were some of the key concepts that we studied. This is something that I want you to remember very well, because it has fundamental, this is one of the true systems level techniques that we studied, right. You can think of networks as being systems level because you look at very large systems and so on, but it is still not very quantitative. So, I think the constraint based models occupy this sweet spot in between oversimplified models and overcomplicated models. You could think of building a genome scale dynamic modeling, which would be dynamic model, which should be the the most accurate or the most reliable model, but it is very difficult to build that, right. So, we had one slide in the middle of the course wherein I showed you right after Boolean modeling or RFBA, wherein we said different kinds of models, what are the size of models that they can handle, what is the reliability, how much inference one can make and so on. I think that is something I would like you to really remember. And then how do you integrate regulatory information or other omics data, right. So, like something like efflux or RFBA, there are many other methods. We also looked at elementary flux modes and several interesting applications. You should remember that slide, right, which says what can genome scale metabolic models tell us, right. It showed about 250 E. coli reconstruction studies that use the E. coli reconstruction to make several predictions, right, about biological network properties, about drug target identification, and then metabolic engineering, so on. So, these are the classic applications that one looks at, right. And then we looked at Boolean networks, right. So, you need to remember about the synchronous update. So, first about Boolean transfer functions. How do you construct these out of biological models? Then synchronous updates, asynchronous updates. We also briefly saw how do you model host pathogen interactions. Then we looked at concepts of robustness, versus evolvability, concepts of neutral networks, and also a few interesting topics such as responsible modeling, when you need to model systems under uncertainty and so on, right? And of course, identifying design principles. How do you, so this is related to synthetic biology, right? So how do you build interesting circuits? How do you build a robust oscillator? How do you build a reliable oscillator, right? And you need to worry about things like retroactivity that we just talked about. Parametric and topological robustness. So another useful concept here that I missed talking to you about is C13 metabolic flux analysis. So that's about a whole lot of topics that we've covered in this course, and I hope you learnt a lot from this course. There are many open challenges, lots of interesting research areas, for very fertile ground for several explorations. We have a lot of interesting projects going on in labs all over India and also in the rest of the world, which try to tackle many of these interesting problems, be it from the perspective of networks or constraint based modeling, dynamic modeling, Boolean network modeling. These are some of the key topics, but there are many more emerging areas like whole cell modeling and so on, and you will see that systems biology has a lot to contribute to biology and the industry, like be it metabolic engineering or pharma in the coming years. So this was the last video in this course on computational systems biology. I hope you enjoyed watching these videos and understanding various concepts. I'll be very happy to continue to interact with you in by email or whatever, and I think this is a very promising field, as we've just discussed. There are many challenges and many open problems for budding scientists to work on. Thank you for taking this course, and I wish you all success.